All right, I'm back. We are on page 253 now. We just finished 252. It's literally 5 minutes after I finished the last video, but I changed my shirt just because I feel like you need a little variety in life. So let's do this. Function graph. What am I doing? Oh, the function f graph below is composed of a line segment, a cubic function, a quadratic function, and a point. You might need that information to figure out some or all of the following limits. I kind of hope we don't, but let's find out. All right, so we're getting really good at this, I think. So limit as x approaches -4 from the left. All right, -4. So I mean, I'm looking for that, but it's not a nice value. So I'm gonna use my thing where I do the slope, right? So if I go over 3, and then what are we going up here? 1, 2, 3, 4, 5. 5/3. Slope is always 5/3, it turns out. I use that maybe too much. So if I go over 3, I'm going to go up 5. So if I go over 1, I'm going to go up 5/3. And I started at -4, which is -12/3 plus 5/3. So I'm at -7/3. -7/3. And then you can see from the graph that the limit from the right, so from the right, is going to be exactly the same, right? Because this is continuous, and the definition of continuity is limit exists, function exists, limit equals the value of the function. 3 parts all the time. All right, limit as x approaches -2 from the left. -2 from the left is, I feel like I should just be consistent with the colors. -2 from the left is going to be that, and that is 1. Limit as x approaches -2 from the right. Let me switch colors from the right. It's like this, and that's going to be -2. So the limit as x approaches -2 doesn't exist because the limit from the left is not equal to the limit from the right. They both exist. They are finite, but they're not equal. That's the definition of a jump. That's the definition of a jump discontinuity. So sometimes you trip over your words, especially when you're saying them really fast. Limit as x approaches -1 overall. I mean, we got a continuity situation here. So that's just going to be 0. The limit as x approaches 0. So this is the limit as x approaches 0. I should have done this on the last one, but this one's more interesting. I need to make sure that the limit from the left, this one, is equal to the limit from the right, which is this one. And they're definitely equal to each other. So the limit overall is that y value. The logical y value is the y value, and it is 2, which means that the function is continuous, right? The limit equals the value of the function, by definition, continuous. Limit exists, function exists, limit equals the value of the function. You should be saying that in your head as much as possible. The limit as x approaches 1. Continuity again. Continuous is the best. So we haven't had a lot of those. Actually, I didn't even look at the value. I just like, yeah, it's continuous. Let's move on. 1, right? The logical y value is the y value, so we get 1. And then limit as x approaches 2 from the left. So why is it only from the left? It's because that's the only thing that makes sense, because the function doesn't exist to the right of 2. So the only thing that really makes sense is to ask you the limit from the left. So we're on the function, we're going this way, and -2, I think, is going to be our answer. All right, I'm going to keep going. I'm going to do the next one. I feel like we're going at a good clip on these because reading graphs is something that you're probably pretty good at. And then this is probably going to be terrible because I'm seeing a trig function here. I didn't tell you it was a trig function, but this is definitely a trig function. So let's see, what trig function is this? All right, so it has a maximum of 3 and a minimum of -1. What I'm going to do here to make my life a little easier, I'm going to dot this in. So this is the kind of thing that you can only do if you made the notes or the person who made the notes is explaining them to you. I know that this is a normal trig function. I just need to figure out which one. So to me, this looks like this point right here is at -pi. And then if I continued my graph, which I shouldn't, but I'm going to do. Let me do it in like, if I continued my graph, it would be like there. And if that continued, I'd go from an intercept to a minimum to an intercept. This is negative sine. This is the graph of negative sine, but not just negative sine. There's more going on, right? We have an amplitude and we have sinusoidal axis, right? So this is y equals, so it's negative 2. I'm gonna say it's 1 minus 2 sine of x. All right, so if it's 1 minus 2 sine of x, then I can find the limit as x approaches -5 from the right. So that from the right means do this, and that means just plug in. So this answer is incredibly gross. It's going to be 1 minus 2 sine of -5. Well, you could leave that, or you could use the fact that sine is odd and say that it's 1 plus 2 sine of 5, which, like, on a multiple choice question, I feel like that's the answer that you would see. Use the even and odd properties like whenever you can. -1 from the left. So -1 from the left. You're on this thing, you're going there. That's the logical value. The logical value, it should be if we plug -1 into this thing. So if I plug -1 in, I will get 1 minus 2 sine of -1, which again, I think would more likely look like that. Nothing we can do about that. All right, how about if I'm approaching -1 from the right? -1 from the right, looks like this. Logical y value, definitely 1. So we're always looking for the logical y value. We don't actually care what the y value is. In fact, often you're not even asked that. You're just like, so your brain is going to want to choose that all the time. Fight that urge. Always go with the logical value, not the actual value. 0 from the left. So here, 0 from the left looks like -1 to me. 0 from the right next. It is 0 from the right. You can see, I mean, you can probably blow through these faster than I'm doing them, which do it. If you can do this faster, do it. So 2 is the logical y value there. The limit as x approaches 1, just overall 1. I'm gonna do my slope thing. So I see that if I go like 3, this is 3, this is 1, well, -1, right? So I'm gonna put -1. If I go over, so it's -1/3. So if I go over 3, I go down 1. So if I only go over 1, I would go down 1/3. So it's going to be 2 minus 1/3. 6/3 minus 1/3 is 5/3. So this will be 5/3. That conversation probably didn't make sense to a lot of you. An alternative way of doing it, which is probably better, is to say that this is y equals 2 minus 1/3 x. And so when you plug in 1, you get 2 minus 1/3. So 6/3 minus 1/3 is 5/3. Either way, it doesn't really matter. I find that over time you become more comfortable with that slope concept, which is insane because you should have been comfortable with that in Algebra 1, but like Algebra 1 is a very overwhelming experience and it takes a while to sink it. 3 from the left. Look at this. It looks like my graph doesn't connect, doesn't it? Like it looks like there's a little hole right there. I filled it in, but I think originally there might have been a little hole. 3 from the left is going to give me 1. I'm just going to assume I'm going to be asked 3 from the right. And if I am, it's also going to give me 1. So let's see if I anticipated that correctly. 3 from the left. Yes. So 3 from the left gave me 1. And 3 from the right, while we were there, also gave us 1, which means the limit exists. But if you go back and look at the function, the value of the function is not the same as the limit. So this is a case where the limit exists and is finite, but is not equal to the value of the function. That is by definition a removable discontinuity. You'll find out later in the notes, but I'm going to tell you right now, I hate the fact that this is called removable because if you try to remove it, try to like fill in the hole there, you don't have a function anymore because the function is up at 3 when x is 3. If I make f of 3 equal to 1, now it's like when x is 3, you have two different values, but by definition, this is removable. So the limits were both 1, and then the limit as x approaches 3 of f of x is also going to be 1, because the limit from the left equals the limit from the right. F of 0 is like an unrelated question, but okay. On our graph, I see 2. So that's equal to 2. And then f of 2, I'm going to use my, so like from this, f of 2 should be 2 minus 2/3. 6/3 minus 2/3 is 4/3. I don't know why I asked that, but I did. I feel like I should have asked you for f of 1 at some point. Like, I feel like that would have been the ideal question. F of 3. F of 3 is what I should have asked you for, and I did. Good job, me. Okay, f of 3, we already discussed this. F of 3 is up here. It's 3 for some reason. So the limit as x approaches 3 is 1. F of 3 is 3, so removable discontinuity. So the limit definitely exists, but it doesn't equal the value of the function. All right, I'm going to stop this video here. I will be back in another video to keep going, and we're going to get through this. So I will see you then.